So we're going to use these very nice diagrams from Dutro and Klein to illustrate the structure of pyroxenes. In this top diagram here, we have the M1, M2 sites and the tetrahedral sites. We'll just draw a T over this little triangular figure right there. So if we write the general formula, we can write something like M2 M1 SiO3, where M stands for a metal cation, and the M2 and M1 are the different sites where those metal cations can be sited. As you can tell, the M2 site is quite a bit larger than the M1 site, the way it's drawn here. The M1 is in six-fold coordination, but the M2, the way it's shown here, looks like it's in eightfold coordination. So we'll draw Roman numeral 8 here, although it doesn't have to always be an eightfold. So let's see how that checks out. For the M2, let's take this guy here. We've got a central cation here that's bonded to an oxygen there, and then another one that is also bonded to an oxygen that's just below at the bottom of that tetrahedra. Then there's another one there, another one there, another one there, another one there at all the corners. So we get 3, 4, 5, 6, 7, and then there's another corner back there. So it's an eightfold coordination. Well, how does this work with the more familiar formulas? You might know pyroxenes as being something like this, Mg2SiO6, or instead of magnesium, you might have iron. So that would be enstatite the way I've written it here, or we might have diopside, CaMgSi2O6 like this. Well, in this case, the calcium, the larger cation, would be in the M2 site, and the Mg is in the smaller M1. Over here, for the case of enstatite, the magnesium is occupying both the M1 and the M2 sites. For the case of enstatite and ferrocylite, all of those magnesium atoms will be in six-fold coordination. So this eightfold part is not necessarily fixed. For the clinopyroxene, something like diopside, then the M2 will be in eightfold coordinations. We could write a Roman numeral 8, but if we're talking about the orthopyroxenes, so for orthopyroxene, the M2 will be in sixfold. So these M2 sites here will be a little bit smaller than what's illustrated here. I believe in the diagram from Dutro and Klein, this is the mineral jadeite, and that is the case for sodium on the M2 site, AlSi2O6. So it's sodium on the M2 site, aluminum on the M1, and then silicon occupying each of the tetrahedral sites. Though we could put aluminum in there as well if we wanted to. So this is an excellent diagram illustrating the pyroxene structure. There's another diagram just below it, also in the text by Dutro and Klein, that shows this. Now let's take a look at the orientation. This is the C-axis that is shown here, up and down, and then B is the axis shown left to right. So what that means is that we are looking down the A-axis. So the C-axis is vertical, B left to right, we're looking down the A. So the A-axis is this axis here coming in and out of the board. How about over here? Take a look. This is A sine B, where B is the angle between the A and C axes, and then we have B again going left to right. Well, this gets this kind of odd value here, not A, but A sine beta, because here we're looking down the C axis. So the C axis here in this case is coming in and out of the board. It's as if we're in the plane of the page here, but we're looking in this direction rather than down on this diagram. We're in the plane of the page looking in this direction or maybe in this direction. That would be the view over here. So we're looking down the C-axis in this view here. So down the C-axis means A is coming in and out of us. Let's take a look at how it translates. So if you look at the dashed lines here, that means we have a tetrahedron that's pointing downward. And then if we have solid lines, which are the case over here with a little bit of shading, the tetrahedra are pointing up towards us. So this guy, this guy, this guy, all those tetrahedra, there'd be an infinite chain, but they're pulled away so we can get a better look at them too. They're pointing up, and then these over here, this fellow, that one, and that one are all pointed down away from us. Let's take a look at how that works. We have these two guys here pointed up, and they're hooked up to an M2 site. There's a very large M2 site there. And so these fellows that are pointing up are adjacent to those M2 sites. And look at this guy pointing down, and those are connected to an M1, smaller than the M2 over there. Here's another octahedral site, M1. So you can see that this guy here shares an oxygen underneath with this M1, and this guy over here shares an oxygen with that M1. So we'll look at the fellows pointing down, and there they are next to the M1. So that's how we get this view over here. It's as if we're looking down the c-axis. Looks like we're looking from the top down rather than from the bottom, and then we would get this view where the fellows pointing down would be to our right, and then the fellows pointing up would be to our left. Is that right? Would it be looking down? No, it'd be looking in this direction here, looking up. So, well, I guess it depends on which side of the chain you're looking at. So that's probably irrelevant. So what they're showing here is that you have this strip of tetrahedral layers. We'll call that a T. And then you have a layer of octahedrally coordinated atoms. We're not really showing their octahedral coordination here. We'll call that O. And then I wrote the C-axis here, but we're going to erase that. We have another T over here. So you have this little TOT strip, a strip of tetrahedra over here, tetrahedra here, and there's an octahedra in between. So you get these little TOT strips. We can see it more easily here, where I've written a little bit less. There's a tetrahedral layer there, layer of octahedrally coordinated atoms, and then another tetrahedral strip there. And these strips tend to define breakage planes or weaknesses, and they're showing that here where we can have cleavage planes that would be outlined along those dashed lines. And here we get this classic circa 90-degree angle cleavage, both between those planes and those planes. Not exactly 90, but ballpark. And then if you're looking down the c-axis, as we are in all these diagrams, again, we're looking down the c-axis, so we're looking at the 001 plane. So we're looking at 001. If this is the c-axis, then this could be the b-axis here and the a-axis here. And so if that's the b-axis, then this face here would be the 010 as it's labeled. This face here would be the 100 also as it's labeled. This face there would hit the A and the B, 110, etc. So we're looking at the 001. And if we saw this in thin section, or if we were holding a sample and we saw this kind of pattern, this kind of shape, and this kind of pattern, well, that would be an indication of the orientation. If you see this kind of pattern in this section, it would be a clue in terms of the direction you would be looking. So this is a very helpful kind of diagram in terms of identifying not just client pyroxenes from their cleavage angles, that classic circa 90-degree cleavage, but it also gives you a hint at the shape and the patterns that you would see, at least in one orientation, if you're looking at a mineral in thin section. And sometimes if you're doing diffusion profile work, you might care a lot about what orientation you're looking at. You don't necessarily need fancy micro X-ray diffraction methods to figure out an orientation. With a little bit of knowledge of crystallography and optical mineralogy, you can detect the orientation by looking at these kinds of patterns, shape and patterns of cleavage, etc. So that's the pyroxene structure in a nutshell, using, again, these very nice diagrams from Dutro and Klein.